my project is over the very unfriendly seating arrangement problem. And this picture on the right is sort of a bigger example. That's kind of the final product that I'll be building to. But this started with the unfriendly seating arrangement problem. And I believe my slide about that's next. Yep, so back in the 60s, a couple of guys proposed a smaller problem. I say smaller just because they were only asking about a table where people would arrive wherever they want to sit. So they're not explicitly trying to sit as far away as possible from each other. And we can go about that more if people have questions. But to introduce the problem and what started this whole question for me was, imagine you have a public seating space that has 7 seats in a row. So to demonstrate that, I've got 7 circles up there, and the white ones are empty. And often in times like this, the first person will pick one of the endpoint seats. And so that black dot represents an endpoint seat being filled. And then the only other rule for this entire paper, basically, is that each new person will pick one of the roomiest spaces. And in this case, there's only one roomiest space, and it's the other end of the row. It's pretty intuitive. So then now you can probably guess that the next person is just going to pick the middle space. And here's the problem with 7 seats is that there's no more spaces left for the 4th person to sit down without being next to somebody else. So we say that the behavior is unfriendly because people will not sit adjacent. And I call it very unfriendly because they're trying to be as far away from each other as possible at every step. And so the unfriendly number, upsilon, of 7 seats is 3 people being seated in the end. And the problem is that we could do even better. If you see here, you can fill the seats with 4 people without anybody being adjacent. And so if people will just work together, but it requires that the middle seat not be filled. So we say that the optimal number, omega of 7, is equal to 4. So in this sense, it's kind of the opposite of social distancing. We're actually trying to pack as many people in there as possible without it being too uncomfortable. But we look at both ends of the spectrum eventually. So the question that I wanted to answer first is, for which lengths of rows is the unfriendly number the same as the optimal number? Because if you assume people are going to be unfriendly, you want to build a row that fits as many people as possible automatically. So if we define things formally, I'm going to skip over most of these, but that's just the definition of a grid. It's about what you think it is. It's a rectangle of seats, and each seat can either be filled or empty. And it's filled if it's 1 and empty if it's not filled. So in these examples, it's just going to be white dots and black dots, or in Python, it's X's and hyphens, which we'll see later. So if every entry is empty, the whole grid is called empty. We're using just the basic distance formula to measure distance. You could use any other distance metric, but this is a squared plus b squared equals c squared, which you see all the time. So the room at any entry is based on this distance, because like if I'm sitting in a grid and there's another person 2 feet away from me, and everybody else is further away than that, it's only the 2-foot person that matters, because I only have 2 feet of room. You just go by the minimum, the distance to the closest person. Then, so I wanted to explain comfortable first, actually. So what a comfortable grid means that nobody is sitting adjacent, basically. For every person, they have at least 1 foot of room. And then a saturated grid is if there's no empty spaces that have more than room 1, which would be a space where somebody else could sit and still be comfortable. So grid is saturated once no more people can comfortably sit. All right, so once we have those definitions, we can formally define our algorithm. So we start with any seating space. In this case, for simplicity, will just be a 1x9 row. So the first step is to check if it's already saturated, because sometimes we don't start with an empty grid, but for the most part, we will. So if it's saturated, we go ahead and end the algorithm. If it's empty, we'll pick a corner first. So it just happens to pick the left one. And then it could have picked the right one, but it would just be a mirror image. Then to see the roomiest spaces, we let R be the maximum room of empty entries in G. In this case, the room is 8, because that's the furthest away from this one. And so that green space is the roomiest space. And then fill one of the entries. In this case, there's only one. You fill one of those entries that has room R at random. So that will happen. And then we'll return to step 1, because now we can go ahead and fill more people. So not saturated, skip step 1. It's not empty, skip step 2. So the most room is in the middle, and it'll automatically be filled. Now we've got a tie for the most room, and it'll have to pick it at random. So, oh, it happened to pick the right one first, but in this case, the other one is still a tie for the most room. So it's going to get filled either way. And so the total number of people filled in the end is denoted upsilon of n, and we call it the unfriendly number. And if it's a two-dimensional thing, we'd, like if it's a 5x6 grid, we have to say upsilon of 5, 6. Now in one dimension, it's always the same. The randomness doesn't actually make a difference, and that's because of something called the split row rule, which we'll talk about in a second. But as you can see here, in the very end, we've got every other seat filled, and that looks just about as good as it can be. So in this case, the unfriendly number is the same as the optimal number, and the optimal number is defined formally over here. Now there's also the minimal number, which is the lowest amount of people we can put in there so that it's already saturated. So that looks something like this, where each person here is taking up both of the spaces next to it and making them uncomfortable. And with 9 spaces, you can do that with only 3 people. Anyway, one second. So moving on. So Benjamin Warren has entered the waiting room. Since I'm a host, I could admit him. Okay, you got it. Okay, thank you.
Don't worry about it. I'll take care of that part.
Sounds good. So when we're looking at the optimal and minimal rows, we can see that for the optimal number, you can fill roughly every other space. When it's even, you can do exactly every other, and when it's odd, you do one more. So that's effectively the ceiling function. And what that means is that the odd rows will be able to seat more people as a fraction than the even rows. Then the minimal number, as we saw, we can saturate 9 of them with only 3, and we will go roughly every third space until we hit an endpoint. Then we might have to do something a little bit different. And it turns out that the multiples of 3 are the easiest to fill minimally, because you just get these units of 3 spaces that you can saturate one at a time, and it's all even. So what does this look like for bigger numbers? I've graphed out the first like 131 seats, and that's a special number, but I guess 133. And you see that the unfriendly number follows an interesting pattern. And when we compare that to the optimal number, which is the ceiling of n over 2, you see that sometimes it meets the optimal number and it is already optimal, and sometimes it's really far away. So to sort of plot that difference, I wanted to plot the, just plot the difference itself. So this red function delta is the difference between omega and epsilon, is how far short it falls of being optimal. So these valleys of that are the most optimal cases, which you can see over here. And it turns out that those happen for n of the form 2 to the k plus 1, and the number directly above that, and the number directly below that. So that's why we have this error term. But like we said, odd optimal numbers are the most efficient. So for the most part, we'll just say that this e equals 0, so it can be odd. And you can see on this graph that they come basically 3 numbers in a row. It's like a little brief period of it being flat. Now, by contrast, the peaks are where it's the least optimal and the most minimal. So, and we can see that it looks like these peaks come right in between the valleys. So I got the idea that they're probably the average between consecutive optimal numbers. And when you calculate that, it boils down to it being of the form 3 times 2 to the k plus 1. And this sort of makes sense because when you look at the shapes of these results, like the 7 case that we talked about, it's always a group of 3 and then a group of 3 and then 1 at the very end. And if you push them in, if you push these outside borders in, if you move this filled seat over toward the middle, it would look almost like the minimal seating we saw earlier, but it doesn't actually matter where they are. It's the same number of people that the unfriendly seating algorithm gives. So, and the minimum numbers are always odd because they're only 1 at a time. So just the proof outline, I'm gonna just go through this pretty quickly, but I'm just gonna prove the optimal case because the minimal case is very similar. But so we want to prove basically that if n is of the form 2 to the k plus 1, then that implies the unfriendly number is the same as the optimal number. So let's start with a row of 17 because that's this form of 2 to the 4 plus 1. So the first one will get filled, we know that, and then the one on the other end. And since it's an odd number, the middle one will get filled as well. And now we can exercise what I call the split row rule, because every empty space on the left side does not care about what's filled on the right side and vice versa, because this middle dot is filled. So its room only depends on the middle dot, not on everything further away. So that means that each one will fill separately. And it turns out that because of this 2 to the k plus 1 form, the subrows that it splits into are also 2 to the k plus 1. They're just the next power down. And since we know that the 9 seat case will automatically fill up, and since the endpoints of the 9 are already filled here, then they'll both fill optimally. And so that's basically the proof. At that point, you can just, use induction on k to go all the way down to the base case of like n equals 5. So now that we're done with one dimension, I just want to quickly zoom through the optimal seating algorithm, sorry, the unfriendly seating algorithm on 2 dimensions. So this is a 10 by 10 grid. We're going to start with one of the corners. So it picks one at random. And at that point, the opposite one becomes filled. And then these two are ties for the most room again. So they're going to get filled, and they get filled no matter what. Now, this isn't the case for very long, skinny rectangles, but for roughly square rectangles, it's always the corners that get filled first. Now, the middle, since it's an even number, is a tie for the most room. So, okay, it happened to pick that corner first, and now these two spaces, the spaces that were ties for the most room, are definitely not ties for the most room anymore because one of their neighbors got filled. So in this case, both of those actually end up getting filled. So roughly half the time, the ties will get completely destroyed, and half the time, the ties are spread out and they'll get filled up anyway. So in this case, we've got ties that are next to each other. So that one will destroy the other tie. And then this one, only one of those can be as well. So, yep. Now, we've got 3 different clusters, and I think this one gets resolved first, just randomly. Yep. And then the one that was next to it can't be a tie for the most room anymore. But these other 2 are not affected. So they're going to get filled up no matter what. And we see the same pattern here. The middle one can only pick one of them, and then the other 2 get filled no matter what. So at this point, we've got a lot of ties. So let's take that idea of some of them filling independently and use it to speed things up. So formally, the set of entries which is tied for the most room is trivially filled if every entry in that set has less room than the minimum distance between these entries. So as we can see here, they come in clusters, but like for these singletons, this dot up here only has room 2. And none of the other green dots are closer than that. So it does not care which one of the other green dots are filled in. So it's going to get filled in no matter what. But these red dots, those actually do care about each other, but they don't care about the other clusters. So only one of each of those are going to get filled. Oh, but no matter the outcome of the red dots, the green dots are all going to get filled. So that's that. And then one of each pair of red dots gets filled. And at this point, we would be done if we required more room. So like for social distancing, if you required up to 6 room, fewer people would be able to sit down. Or if you just require the square root of 2, this would be the last step because we wouldn't allow people to sit catty corner. But we are, so all of these seats are potential ties for the most room. And again, only this group really cares about any of the others. So all the other dots will just get filled up no matter what. And the red dots will only pick one of them. And now we're finally done. This is the final result of the very unfriendly seating algorithm. And in Python, it speeds things up to have a computer compute it. So I denote it like this, with an X being a filled person and a hyphen being an unfilled seat. A filled person, I mean a filled seat. So we had some random decisions to make along the process of the algorithm, and in 2 dimensions, it actually makes a difference, unlike 1 dimension. So here was the fact that here's the result we just got with 38 people seated, but you could have up to 42 people seated, or as few as 34 people seated. And in this case, the 2-dimensional gamma or epsilon variable is not a function, but it's a random variable, and random variables have probability distributions. So I ran 1,000 trials on the 10 by 10 case, and these are the values I got left. So I had over 250 results with 37 and only a couple results with 42, but still you have sort of this skewed right distribution. And in my thesis, I did all the way up to gamma 1313 like this. They're not all skewed right, and some of them are actually completely the same number every time. And we'll look at that in a second. So we have the unfriendly seating. What about the optimal seating in 2D? And it's almost the exact same. So if you have a grid of seats, you can fill basically every other one like a checkerboard. If it's even, it's very simple. You just get half the seats. If it's an odd number, you could get this half or you could get this half, but the half where you include the corners is always better. So you can round up from half essentially. So again, it's the ceiling function of the total number of entries divided by 2. Now, minimal seating is not quite as simple, and we'll talk about that after we talk about the critical square grids, because this is sort of a powerful tool we get in 2 dimensions. We don't quite get the split row rule because things interfere with each other a lot more in 2 dimensions, but for a very special form, n equaling a times 2 to the k plus 1, I'm calling that a critical square grid. And then the set of entries with coordinates that are multiples of a is called the critical set of G. And the reason this is important is because the very unfriendly seating algorithm will always fill the critical set first before anything else. So here's an example. The H's just represent a tie for most room, like the green dots, but the X's are filled seats, and they fill every third seat in a checkerboard pattern, and that is the critical set when A equals 3. So no matter what, those are going to get filled first, kind of like the very first steps of the one-dimensional case. And if these squares are small enough, they're 3 by 3 right now because A is 3. But if they're small enough, then they'll still be invariant because these ties will be closer to the corners of those boxes than they will be to each other. Now, if these boxes were bigger, if they were 7 by 7 or so, then the insides will still interfere with each other potentially, as long as the boxes aren't of the same form. But that's more of a technicality. So if A is just 1 or 2, then it's again of the form 2 to the k plus 1. And in this case, it actually turns out to be optimal because these squares will just have one tie in them, and every tie will be filled, and it'll just be a checkerboard like we just saw. So when we talk about minimal squares in 2 dimensions, the algorithm does not actually give the minimal seating space. So if we just look at the 7 by 7 case, this is one potential outcome we could get. And it's always 17. It might have a different shape, but the epsilon of 7, 7 is always 17. But this is not the most minimal seating possible. We found out that you can actually seat it with just 14 entries if you order them like this. And in general, you can seat them with roughly a fifth of the entries because each entry is taking care of the ones directly adjacent to it. But that's only for the middle of a big grid. On the border, it's a little more complicated. Either way, it's more efficient than the unfriendly numbers, so we only call them pseudo-minimal squares. Now, I'm going to speed through most of this because it's mostly just kind of fancy, fun results at the end. So we know that it's invariant, but the pattern varies. So it varies because these pockets can only resolve along one diagonal or the other, and we'll see that in a second. So there's 2 options per cluster, and there's 4 to the power of k clusters. So there's 2 to the power of 4 to the power of k possible patterns, which gets really big really fast. So there's 16 total patterns for k equals 1. There's a pattern with none of them going to the center, and I say they're not going to the center because these diagonals point beside the center. They're parallel or perpendicular. But you can tell none of those diagonals are going toward the center. And then there's one where they're all going to the center. And then there's one where one of them are going to the center, but you can actually rotate this 3 different ways because it could be this one or this one or this one that's not going to the center. So that makes up 4 out of the 16 patterns. There, by symmetry, there's where one of them is not going to the center, or 3 of them are. That's also 4 out of the 16. And then there's one where 2 of them are going to the center, which are opposite each other, and you can flip that. But if you rotate it twice, you just get the same thing. So that's only 2 out of 16. And then there's one where 2 of them that are adjacent are going to the center, and you can rotate that 4 different ways. So even though there's 16 patterns, there's only 6 of them up to symmetry. Now for bigger squares, oh, sorry, I want to talk about coloring them a little bit first. And anybody who's familiar with graph theory, like most of the people in Houston's lab, will know what coloring is maybe. We don't actually talk about coloring, but so a set of, okay, sorry. So when you see a filled result of the VUSA like this, you can kind of see how these empty spaces form little hallways, and the filled spaces are like walls between the hallways, almost like a maze. So I call these sets of contiguous empty spaces sections of the grid. And you can say that they're adjacent if they share a wall, but not a corner. It's kind of like a political map, like some states are not adjacent if they only share a corner. And then you naturally get a plane graph, which corresponds to the picture. And I label this just using reading order. So this is section A and B and C and D, just going left to right and reading the empty spaces. Then if we want to color things to give a proper coloring, we don't want to have any vertices be the same color if they're adjacent. So I just programmed it with a greedy coloring algorithm. And so this is the list of colors I used. So A is first, it can be red. B can't be red, so it has to be green. C can't be red, but it can be green. And then D can't be red or green, so it has to be yellow. And then Python spits out this. So you can apply that coloring back to the sections. Now, when we look at that bigger and bigger, this is the k equals 2 case being colored in. And that's the k equals 3 case. And these have, k equals 2 has over 65,000 patterns. And then k equals 3 has over 18 quintillion patterns. It gets really big, really fast. And now we finally get a blue square. So the greedy coloring algorithm required up to 4 colors to be able to color this in. And then I shortened the algorithm a little bit and was able to get a a 49 by 49 grid colored in, which you might recognize from the first page. But basically, the 4-color map theorem says that you should be able to color this with only 4 colors. But since the greedy algorithm gives us a 5th color, that means it's not what you call well colored. And that's about the last result I got to before I started actually putting it all down on paper. And this is just a really insanely big amount of patterns. So potentially it's not going to be that easy to classify them. But on the note of that, I made a list of open problems that we could do, including improving the algorithm time, looking at higher dimensional squares, looking for bigger patterns, like I just mentioned, looking for non-square grids or just arbitrary grids, and treating these probability distributions and analyzing them with their expected value and variance, higher room requirements, like for 6 feet in social distancing, and different distance metrics. And that's all.
Okay. But let me ask you if you considered in your treatment of this problem, if your 2 dimensions had different constraints, so that the unfriendliness behavior would be limited to one of the dimensions. And I'm trying to translate that type of mathematical problem into real world behavior, in the sense that people treat sitting next to someone a little bit differently from sitting immediately behind a different person.
Yeah, like in a movie theater, you've got seat backs,
right?
So you're not as bothered by the person behind you as you are, or in front of you, as you are by the people next to you. So no, I haven't actually considered treating vertical and horizontal distance differently. That's a great question. And I talked a little bit about, like, this model only actually looks like the real world in very simple cases. So there's a lot of ways where it could be expanded or more variables could be added. Like for a movie theater, you could assign sort of a value to each seat based on how close it is to the center or where the best view of the screen is. Because in movie theaters, people don't go for the corners first. And people often arrive in groups, or if a space is big enough, like if you had a bathroom that was 100 urinals long, nobody's going to walk all the way to the 100th urinal. They're just going to go maybe like 10 or 12 spaces away from somebody else. So different like variables to actually model human behavior. That might be more of an applied math type of problem, but it's definitely something that this could be expanded to.
So thank you for that answer. I do have more questions in my mind, but I will defer. I will wait on that if we have more time later.
Okay. Yeah.
So thank you again, Isaac.
Everybody else's project. Yeah, no
Absolutely.
problem. Thank you for posting and having questions.